Next, we're going to talk about another very important aspect of this theory called NP completeness. This starts with a very simple definition. So any search problem, a problem in NP, is said to be NP complete if all problems in NP polynomial time reduce to that problem. This seems like a very, very strong condition, but actually it's pretty natural, as we're going to see in just a second. And the reason this class of problems is important is that there's a theorem that was proved independently by Cook and Levin in the early 70s, really about the same time as Karp was doing his reductions for practical problems, that says that SAT is NP complete. Now, this is a result with amazing ramifications. In a course in theoretical computer science, you could learn this proof really in an hour. And I don't have the time to go through it in detail, but I can explain the basic idea extremely briefly. And the idea is to take the idea of a non-deterministic Turing machine, which is like a specification of an algorithm of a search problem. You take your problem and you formulate it as a non-deterministic Turing machine. And that's true. Any search problem, you can do that. That's kind of the formal definition of a search problem. And what the proof does is take that notation, which is a particular notation. You could think of it as a mathematical notation or states and arrows the way we do it with labeled transitions, and just convert that notation into SAT notation. They're both kind of discrete formalisms, not really that long or difficult. But that's what the proof does, is get to the point where given any search problem, you can make a non-deterministic Turing machine, and then you can convert that into an instance of SAT, which means that if you have an efficient solution for SAT, then you have an efficient simulation of that non-deterministic Turing machine, which gives an efficient solution to any problem in NP. So non-deterministic Turing machine goes to SAT instance, and that's the reduction. And again, I'm very, very much oversimplifying this proof. It's really an amazing fundamental result. The corollary to this means that SAT is tractable if and only if P is equal to NP. Of course, if P equals NP, it's tractable, but also if SAT is tractable, then all the problems in NP are tractable. And that means P equals NP. Or another way to do it is to say, that assumption that SAT's intractable is very much the same as assuming that P is not equal to NP. And in terms of the practical problems, here's what this theorem says. It says that all those problems of Karp's are going to reduce to SAT. All problems of NP reduce to SAT, but then SAT reduces to all of them. So what this means is that all the problems are NP complete, not just SAT. If we can solve any one of these problems, we can solve all the problems in NP. That's a much, much stronger statement about the difficulty of solving these problems. They're all NP complete. And all of those thousands and thousands of problems that are formulated in scientific papers every year are NP complete, in the sense that if you can find an algorithm for any one of them, you have an efficient algorithm for all of them. That gives us much more confidence about asserting the difficulty of finding guaranteed polynomial times algorithm to solve them than just mere reduction. So NP completeness adds to our universes in the following way. If P is not equal to NP, then there's some intractable problems. If it's equal, there's no such thing. Non-determinism would help. If it's equal, non-determinism no help. And again, these are the different formulations that we looked at. If P equals NP, it's no harder to find an answer than to just guess it. And if P equals NP, then there's guaranteed polynomial time algorithms for all the problems in NP. If it's not equal, then you can prove a problem to be intractable by doing a reduction from an NP-complete problem. So the situation is a little bit more like this. And that, again, these are possibilities just based on the basic definitions that we have. But still, there's no progress on knowing which of these two things are true, despite the fact that many people have been working on it for decades. So just a quick summary. We have the class of all search problems, that's NP, the ones we can solve in polynomial time. Those are P, and then we have the NP complete problems, which you can think of as the hardest problems in NP. And then the idea of intractability, which if P is not equal to NP, those are the ones that are not NP. And we have thousands and thousands of problems that are NP complete. And our idea about this theory is to use it as a guide when faced with a practical situation. If you have an NP-complete problem, you need to know that finding efficient algorithm, guaranteed polynomial time algorithm, for that problem would be a stunning scientific breakthrough. It would be a proof that P is equal to NP. And you should know that because you definitely will confront some NP-complete problems in your career. So it's pretty safe to assume that P is not equal to NP and that the NP-complete problem is intractable. And so what you want to be able to do at a minimum is identify these situations and proceed accordingly. And we'll talk about ways of doing that in the next segment. In the meantime, if you're in Princeton, if you take a look at the west wall of the CS building, you can see some indentations in the pattern of bricks. And this is made for really students of this course. If you take those indentations and treat them as binary numbers, convert them to ASCII, then you get the P equals NP question. Now, when this building was built in the late 80s, a lot of people said the building's going to last a long time. Why would you put a question, such important question that so many people were working on, into the brick? Actually now, a couple of decades later, it's more important a symbol than ever of computer science. And of course, with just investing in a few bricks, we could change the equals to a not equals and or the question mark to an exclamation point without much work.